Okay, so in this video, we're going to be taking a look at independent events in probability and how we can use probability trees to help us put together questions, figure out what is being asked of us, how we can work things out, all of these kinds of things. Okay. Probability trees by themselves are a method for doing questions. You don't have to use probability trees in order to get to an answer. In fact, later on, we will be looking at trying to do some of these questions without probability trees. But to start off with, they are a great way of getting us to think about what probabilities do we have, what do we need, what is a question asking for. Okay. But before we get into dealing with probability trees, we have to think about some of the other things that we will have heard about before as well. Okay. The first thing is what an independent event is. Now, an event is just something that can happen. Independent events are events that have no impact on one another. Okay. So if one thing happens and that doesn't affect how something else will happen, then those two things are independent events. Okay? It's slightly different to how mutually exclusive events are. Mutually exclusive events are things which cannot happen at the same time. Okay? Independent events could happen at the same time, but they don't impact one another if they do. Okay? So that's one thing. Independent events do not impact one another. In probability, if we're saying something and something else, when we're dealing with events like these, that's essentially keying us to do some multiplication. And in probability, if we've got the word or in situations like these, it's keying us up to do some form of addition. Okay? So we're going to be using these two facts quite a lot, okay? And for what we're going to be doing today, these two things are going to be quite important. And also, this will be important as well. Okay? So, tree diagrams. Tree diagrams are useful to help us understand probability. They're not essential for these problems. And what they gear us up to do is they gear us up to think about what are the different outcomes that we could have and what are the probabilities of having those outcomes happen. Okay? And in any instance, we should have the branches coming off at a joint should add up to make one. Okay? And we'll see this in action later. If they don't, we have an option missing. Okay? And if we look to chain some branches together, again, we'll see this happening later, this represents us thinking about a combination of things happening. Okay? And the first example that we're going to look at is we're going to look at the kind of simple example of us flipping a coin. Okay? So when we're flipping a coin, we have to think about what outcomes we could get. Well, if we take a coin and flip it, we could either have a head or a tail. So our first throw, those are the two possible combinations that we could have. We have one universe where we get a head, one universe where we get a tail. Okay, it's something, you know what I mean. Now, if we then take the coin and flip it again, we're going to have some branching off scenarios. Okay, after I get that first throw, let's say I got a head. I then take the coin again, I flip it again, and I could get another head or tail. If I take that coin at first and I flipped it the first time and I got a tail, the next time I flip it, I could get a head and a tail again. Okay, the fact that I threw a coin the first time doesn't impact what will happen the second time I throw it. Okay, it's what we call an independent event. Okay, now they have no impact on one another. Me throwing the coin the first time has no impact on what I will get on the second throw. Okay? And because this is a normal coin, there are two outcomes. The probability of me getting a head or a tail is just a half. Okay? So on any of these branches, I'm just getting a probability of a half. Now, say that we wanted to think about what the probability of getting a head and a tail in that order. Okay, so the probability of us getting a head, then a tail. So the way that these probability trees work is that we would multiply along each of these branches. Because think about what we're saying. We want the probability of a head and a tail. Okay, a probability of a head and a tail means we multiply those two probabilities together. So I'm going to have a half times by a half, which is just a quarter. Okay. Now, looking at this example, you might be able to say, well, no matter which one of these branches I'm going to go down, I'm always going to be doing a half times a half. And you'd be right, because that's what a fair coin does. Okay, so it's actually more interesting if we look at a situation where these probabilities are not the same each time. So this time we have a coin which is biased. Okay, that means it favors one particular result. So the probability of throwing a head each time is now 2/3, not a half. Okay, so we're more likely to get a head. Okay, it could be like it's a weighted coin. Okay. So the setup for our probability tree is going to be the same each time, but now the probability of throwing a head will be 2/3. The probability of us getting a tail will be 1/3. Okay, because these are mutually exclusive events, they have to add up to make one. They cannot happen at the same time. Okay, so then on the second throw, we would have the same probabilities because coin throwing is an independent event. It doesn't affect the next flip, whatever we got on the first flip. So our probability tree would look something like this. Now, calculations here do become a little bit more interesting. Okay. So, this question here, what is the probability of getting a head, then a tail in any order? Well, hang on a minute. If we're wanting a head, then a tail, then the order does matter, doesn't it? So, let's go for that. We want a head, then a tail. Okay. So, a head, then a tail would be going a head, then a tail. Okay, a head and a tail. So probability of H, T would be 2/3 times by 1/3. Okay, 2/3 times by 1/3 is 2 times 1, 2, 3 times 3, 9. Okay. Now, if we wanted to look at the probability of getting a tail, then a head, okay, we'd have a tail times a head. We'd have 1/3 times 2/3, which again is just 2/9. Okay. What is the probability of us getting two of the same type in a row? Okay, well, the probability of us getting two of the same type in a row would be looking us at getting the probability of a head and then a head, but also getting the probability of a tail, then a tail. Okay, think about what it is we're asking us to find out here. The probability of a head and a head, or the probability of a tail and a tail. It doesn't specify what flip that we get. It just says getting two of the same type in a row. Okay, so either a head and a head, or a tail and a tail. So for these, we're going to need to work out these top and bottom branches. Ahead and ahead, so probability of getting ahead then ahead, is 2/3 times 2/3, because we just multiply those two branches together. 2 times 2 gives us 4. 3 times 3 gives us 9. Tail and a tail, down at the bottom of our tree diagram, 1/3 times 1/3. 1 times 1 is 1, 3 times 3 is 9. So the probability of us getting two of the same type in a row is going to be 4/9 from up here plus 1/9. 4/9 plus 1/9 is just 5/9, which we can't simplify, so we just leave that as it is. Okay, so thinking about what the question is asking us, and also having the diagram out to kind of help prompt us, can help us getting these questions together with some degree of ease. Okay, getting the diagram, getting the probabilities is certainly step one. Working out the probabilities for the events that we need, step 2. Then if we need to think about what kind of events will we need to work out the probability, and if we have more than one event that we need, adding the two things together. Okay, so let's change that back to red. And the probability of getting a head then a tail was 2/9. Okay, we're just looking at that one up there. Okay, so so I would like you to take a moment and have a look at this question, give it a go. You're probably looking at about 4 to 5 minutes to have a go at this question. Okay, getting the tree diagram together and having a go at part B as well. About 4 to 5 minutes. Okay, I'd recommend stopping the video at this point, having a go at the question, and then resuming afterwards so that you can follow with the solution. So, chance to pause. Okay, and I'm going to be going through the solution now. So I've got 10 pens. 6 of the pens are black and the rest are green. I remove a pen without looking and I make a note of the colour before putting it back. Okay, that's going to be important. I then choose a second pen, okay, at random, okay, without looking. So I want to draw a tree diagram showing all the possible outcomes, okay. Well, first thing that could happen is that I could, dip a hand into my pot of pens, and I could either have a black pen or a green pen, because those are the only two options that I've got, black or green. Now, 6 of my pens are black, so that means that out of the 10 pens that I've got, 6/10 of them are black. That's my probability. Okay. Now, when I put that, I take that pen out, I make a note of the colour, and I put it back, which means that the probabilities the second time round are going to be the same as the probabilities the first time round. Okay, because I've put the pen back. The same number of pens are still there. The same colours are still there. Okay, so thinking about the probabilities that I've got, first time round, the probability of me getting a black pen is going to be 6 out of 10. Because there are 6 black pens, 10 in total. The rest are green, so that's 4 green pens out of 10. And in the second choice, because the pen was put back, the probabilities are going to be the same. So there's our tree diagram. Okay, we just interpreted the question, thought about what options it is that we have, put the probabilities in. Now the part B, what is the probability of him not getting a green pen in his 2 picks? Okay, so let's have a look at all of the different scenarios that we've got. I do not want a green pen. Okay, well that automatically rules out this bottom section because I get a green pen in my first go. So if I don't want a green pen, I can't have black and green. The only way of me not getting a green pen in my 2 picks is to go black then black. So this thing here is going to be the probability of me going black and black. So here we multiply along these 2 branches, so 6/10, so probability of black then black is going to be 6/10 times by 6/10. 6 times 6 is 36. 10 times 10 is 100. So I've got 36 out of 100, which I can simplify, so, you know, I really should. So let's divide both of those by 2 to get 18 over 50. We can divide by 2 again to get 9 over 25. And that's as far as we go. Okay. So that is all that question was asking us to do. It's quite nice. You don't have to use a tree diagram, but at the moment we are, just to get used to what the probability is asking us to do, what we're looking to find out as well. So one final question coming up for this video, one for you to have another go at yourself, and then go from there. So this is the question that I want you to have a go at now. Okay, and we're dealing with a very similar scenario. Okay, we want to try and construct a tree diagram and then answer the 2 questions underneath. Okay, so I'm going to give you a chance to pause the video, have a go at that question. Okay, had a chance to pause it. I'm going to start going through the solution now. So Rebecca has got 9 coloured beads in her bag. Okay, 4 of the beads are black, the rest are green. Okay, just as we had in the example before. She removes a bead at random and then notes the colour before putting it back. She then chooses a second bead, just like we had before. So we've got 2 options that we can have first of all. In her first pick, she can either have a black or a green bead. To start with, 4 of the beads are black, and there are 9 coloured beads in the bag. The rest are green, so that means that 5/9 of the beads are going to be green. We then remove a bead at random from the bag, yep, and she puts it back and chooses the second bead. So then she has 2 more options coming out of black and green. The colours have not changed. And because she put the bead back, the probabilities haven't changed either. So our probabilities are just going to be as they were before. There's our tree diagram. Calculate the probability that Rebecca chooses a green and a black bead in that order. Okay. And then 2 beads of the same colour. Okay. So let's have a look at that first question. A green and black bead in that order. There's that keyword and. Okay. Gearing us to do some kind of multiplication. A green and black bead in that order. The order matters, so green, then black, a green and a black. So this one, which I'm going to do in blue, gets us to this scenario here. So the probability of us going green then black is 5/9 times by 4/9. 5 times 4 is 20. 9 times 9, 81. That's all we need for that first one. Okay. For the second part, 2 beads the same colour. Now for this, I could have 2 different scenarios. I could either have black and black, or I could have green and green. Okay. So for this one down here, that is the worst star symbol I've ever seen. I have 2 beads, same colour, so I could either have probability of black and black, or the probability of green and green. So I need to work out what those probabilities will be. Black and black will be this top one. 4/9 times 4/9. 4 times 4 is 16. 9 times 9 is 81. Green and green is down here. 5/9 times 5/9. 5 times 5 is 25. 9 times 9 is 81. So for these two things, I'm going to add them together. So I've got 16 over 81 plus 25 over 81. Okay, the fractions have the same denominator, so I can just add those two things together. It's going to be out of 81. 16 plus 25 is going to give us 35, 41. 41 over 81 definitely doesn't look like it can simplify, so I'm just going to leave it like that. Okay. Now, I'm going to just add one extra thing to this, okay? What if it said a green and black bead in not that order, but any order? Okay. Well, if we wanted that, I wouldn't just have the probability of me going green and black. I would have to add something else to that. Because I could have a green and black bead, but I could also have a black then a green bead. Because I can have them in any order. Okay. Okay. So I would have to find the probability of both of those events individually and then add them together to get my probability of getting a green and black bead in any order, as opposed to what we had before, which was in that specific order. Okay. So that's kind of a quick introduction to looking at probability trees. Okay. This deals with things where we replace them, where the probabilities are the same each time. The difficulty that I think most students have with this is trying to interpret the question and making sure that they select the right probability. Okay. If you look at the question carefully and you see that you may need to have more than one branch added together in order to make that thing happen, then make sure you do that. Okay. Other things that I would suggest as well are look carefully as to see whether the question is saying that you don't have a green bead or you don't have a black bead, and think about which branches do you have to travel along to have that thing happen. Okay. Drawing the tree diagram will help. Okay. But as I say, once you get really into these kinds of problems and you get really practiced with them, you can manage to do them without the tree diagram. Okay. Now, some tree diagrams can get really kind of complicated, and the question will kind of not really make that too obvious. So what we're going to look at in our next video is what I call a yes-no probability tree. It means either it does happen or it doesn't happen. Okay, and that can make things a little bit simpler for us to view. Okay, but to get started with these kind of problems, that's the kind of thing that you'll need to think about. And just as a kind of a language-based thing, okay, and different ways that it could be written, if I'm saying probability of one thing or another thing, so like 2 greens or 2 blues, I would want to add those 2 probabilities together. If I'm wanting probability of one thing and another thing, then I'm dealing with those things multiplied together, and this is generally when they can only happen when things are mutually exclusive. They cannot happen at the same time. Okay? Some of this notation might be a little bit tricky if you've never seen it before, but think about the language of what you're asking yourself to find out. Okay? One thing or another thing, you're looking to add them together. One thing and another thing, multiply them together. Okay? Try out the Heggerty quizzes that we've set online. Try out some of the textbook exercises if you're wanting that little bit of extra practice as well. We'll have a look at some more of these kinds of problems in another video. And sorry this one couldn't go live as it should have done. I've been having some weird problems with my streaming software today. Okay. I will see you in the next video. Take care. Bye-bye.